So, as we all know, not all countries are blessed with conventional hydrothermal resources. So, however, with our new technology and innovation, we are hoping to be able to develop geothermal on a grand scale using enhanced geothermal systems or in areas that we have not really thought of before. So that being said, I'm gonna ask the four speakers to present their talk. I will allow 1 or 2 questions at the end of each talk, and if we have time, we are 10 minutes late already, but hopefully you will forgive me if I take the extra 10 minutes into the lunchtime. But if we have time after the lectures, I may call upon them here on a panel to ask for you to ask them further questions. However, the first one to present is Mariane Peter-Borie, and she will be talking about breaking through to new green frontiers by harnessing offshore spreading center geothermal energy. This is very exciting. I find this field of geothermal exploration extremely exciting. But Mariane is a geothermal technical specialist in the geoscience new venture at CGG. She has been working in the deep geothermal energy field for more than 15 years as a researcher, and she has been involved as a geologist and rock mechanic specialist in many projects in different geothermal play types. Welcome.
Tack för er. Thank you very much.
Okay, this is not working yet, but...
So I can use this one. Thank you very much.
I think so.
So good morning, everyone. Thank you for attending this presentation. I would like just to start by asking you a question. Have you ever asked yourself what kind of ancestor you'd like to be? Maybe the one who will break through new technology, new frontiers, new adventures. And actually, when I joined CGG a few years ago, the team, my colleagues, Robs, Becky, Alex, and many others, they taught me about offshore geothermal. What a crazy idea, offshore geothermal. But actually, I liked it. What's challenging, and why not? As said by Mariette this morning, we need countries reaching the 100 gigawatt club. So maybe a part of the future green energy mix look like this. I mean, harvesting directly the heat, the earth energy in the oceanic crust. So the target could be directly the basalt, the pillow basalt, the layer 2A for one who are familiar with this denomination, and trying to extract directly the heat. And we have heat thanks to the insulation by sedimentary layers and heat coming from the spreading centers, and being able to harvest it, and for power, but also for green fuel like hydrogen. But back to basics. Oceanic crust, it's almost 60% of the Earth's surface. It's a huge area, and it remains largely unexplored. We know almost nothing about oceanic crust, but we have evidences of hydrothermal circulations. Thanks to the data, we have, it's a small amount compared to the surface of the ocean, but we have some. Does it work? Yeah, okay. So we have something like 97,000 data offshore. And in this data, we have heat flux measurements, temperature measurements. If we are lucky, we have well bores with permeability, porosity, and so on. And thanks to this data, we know that we have hydrothermal circulation. And we have also more natural evidence, like all the hot vents, black smokers, white smokers, existing around the different oceans all over the world. So that's evidence that hydrothermal circulation, geothermal reservoir exist offshore. And based on this data, we performed numerical modeling, thermal numerical modeling, in order to assess the potential for geothermal, offshore geothermal. And we are pretty confident that there's a resource. The resource exists. And thanks to the modeling, we have perspective areas that are really likely to deliver a huge amount of energy, like, for example, Red Sea, Gulf of California, and, of course, Iceland as well, because it's directly on the ridge. So I would like to talk about this graph. It has been published by Wilmarth in 2020, and it's really, really interesting. But you're probably aware that rift systems onshore are the ones who deliver the biggest power density. Highest temperature, biggest power density. And we have a really good example here in Iceland with Helsinki, Reykjanes, Kaplan, Svartsengi, for example. So we know that onshore, actually, the rifts are probably the best target for delivering the huge amount of energy we need for achieving the energy transition. And offshore, it will be the same. In addition, what we know is that usually onshore, in high temperature settings, such as rift, the wells are usually self-flowing, pumped for the lower temperature, self-flowing. But offshore, we have the opportunity to add pumps to deliver a bigger flow rate for each well, because offshore, thanks to the experience from the oil and gas industry, we can put all the electronics outside of the well, outside of the riser, and we can extract more fluid, more heat on this kind of settings. Why it's important as well to go onshore? What would be the benefit to go offshore? So onshore, we have, here you can see them, I will move a little bit, yeah. So you can see, that's the boiling curve. It means offshore, we know that the boiling curve is something like that, with the increasing of the pressure with depth. We have liquid phase with highest temperature, with highest depth. So that's what is currently the case onshore. And the fact is, if we want to reach supercritical fluid, for example, onshore, we need to go quite deep because it will be more than 220 bars, something like that, and a really high temperature. But if we move, and it will be in area where we have a really low permeability, but if we move offshore, what's happened? Thanks to the water column, the pressure will increase. It means that for the same depth, for the same temperature, instead of having steam, we can cause some corrosion issue at the surface. We can have fluid at the same temperature, at the same depth, thanks to the shift of the boiling curve, thanks to the water column. And in addition, really interesting fluid, which is the supercritical fluid, can be reached at depths that will be shallower because the water column will add pressure. For example, if you have 1,000 meters of water column, you will add 100 bars into your reservoir. So that's a really beneficial thing to go offshore. So going offshore, what are the fundamentals, the basics? So the fundamentals, the idea, the concept is First, to extract the heat, so we expect to have at least 200 degrees, but probably more, extract the heat directly from the oceanic crust, from the pillow basalts in the oceanic crust directly, insulated thanks to few hundred meters of sediments. In liquid phase, at the surface, we will have multi-phase, and all the corrosive element will stay in the condensate. We can run a turbine and create power. That's the basic. We will have power. And with the brine, we can re-inject the brine directly in the sedimentary layers or in the basaltic layers. Actually, the recharge of the reservoir is ensured by the ocean itself. So that's the basics. And thanks to the steam, we will have fresh water directly created. So what we can do when we are close to the shore, what we could do when we are close to the shore, we can just have a cable to bring the power to the shore. And what we can do with the fresh water created from the steam, so no need a big plant to condensate that. We have the ocean. It's enough to cool down the steam. We can use a pipe to drive the fresh water directly to the shore. That could be really, really interesting in arid setting, notably. Where we are in remote settings, that's really, and could be also in close to the shore as well, but more interesting things. We are going to create fresh water and we have power. What we can do with fresh water and power, we use electrolysis and we can create hydrogen. Hydrogen can be the fuel for tomorrow and will be the fuel for tomorrow, a green fuel. So we will have a green way to create hydrogen. And then we can ship the hydrogen to the shore. Other use, for example, if we use the nitrogen from the atmosphere, we can create ammonia as well. We can ship it as well, and many routes. CO2 is still a big issue, but we can use this kind of facilities to store the CO2 in the basalt directly, where we have. It's moving. Where we have our wells, when the well is cooled down or whatever, we can re-inject the CO2 and store it directly in the basalt. We can use CO2 as well with the combination of hydrogen to create methanol. And we can also use CO2 and the brine itself, to fertilize the deep ocean, the blue ocean, which is mainly desertic offshore, to fertilize and to create an alga bloom that will trap the CO2 as well. Hence fishery, we can create hence fishery as well in this kind of area. And so many routes. And the brine, it's analog to black smokers and white smokers, so probably a lot of potential co-projects that could be extracted from this brine. So there's multiple routes of commercialization for offshore geothermal, from power, fresh water, hydrogen. The flexibility is the strength of the offshore geothermal. And another point I would like to highlight as well, because we talked about that this morning during the main conference. It's about the risk. For example, in Iceland, when you have a volcanic eruption close to your facilities, you can't move your facilities. You just cross the fingers. Here, because all the plants, all the facilities will be on floating barge or floating vessel, you can move if there's any environment or any natural disaster. So, another point really interesting, and it will be maybe the first question that will arrive in your head when you are going to talk about offshore geothermal, is the cost. And it's a real question, it's a real topic. Actually, can it compete with onshore technologies? So we perform some techno-economic studies. I will give you an example in arid settings for fuel, for green fuel, in particular, I can't disclose the numbers, but we try to transform the numbers into bars, so you will have an idea of the different values. So offshore and onshore, the comparison of both. Offshore, for sure, exploration, drilling will be more expensive. That's the point. And if you compare the price of offshore geothermal and, for example, onshore wind and solar, for sure, offshore geothermal will be more expensive. But if you take into account the other facilities and the different routes of commercialization, and in this case, especially for the green fuel, you need fresh water. Offshore, it will be easy to condensate your fresh water and to perform your electrolysis. Onshore, you need a desalination plant, you need batteries because wind and solar are intermittent. In addition, you have to use land. And land, it's really difficult to estimate the cost of land because it's not only a question of money, but land has a social, environmental, political cost as well. And then you can create your green hydrogen and green ammonia. In added value of offshore geothermal, we can have other potential benefits on the same plants, like methanol. So I touched on that in the previous slide, but methanol, CO2, enhanced fishery, CO2 storage, co-production of elements from brine, and the technical and political value of mobility of the facilities if needed. And if you are finished with one project, one site, you just need to move your plant to another site and no need to build another one. So a key thing to decrease the cost of offshore geothermals as well is the exploration, because we need a high probability of success in this kind of settings. So for that, we need relevant, efficient exploration workflow. And the exploration workflow will be based mainly on seismic images, seismic acquisition, and seismic images. The seismic images will give us the location of our target, depth, the top and the bottom of our targeted layer, but we can have other derivatives such as porosity, permeability, and so on. And in addition, we can use other methods like electromagnetic methods, CSEM, for example, offshore CSEM, and to have an idea of the thermal component of the system. And we can use seismic data to guide the inversion of electromagnetic data. So you have an example here published by Mackie and I in 2020 of what is CSEM inversion without knowing anything about the system, and an inversion guided by the seismic image. I don't talk about the picking of the different layers, but directly guiding by the image. In the framework of another project for deep sea mining, actually, CGG processed 2D seismic lines on the Mon Ridge, so North Atlantic slow spreading ridge, to have an idea of the best location for sulfides that could be mined in this area. So what is interesting here is that we acquired new 2D data, we reprocess them, and thanks to CSEM as well, we were able to identify and to highlight hydrothermal circulation in the area of the ridge. So in this area where you have the red dotted line, that's moved a little bit, but it doesn't really matter, it's still igneous rock, basalt. And you can see the lateral variation in the resistivity that are indicators of hydrothermal circulations. And when we have a closer look to the images associated with this area, we can see that the processing, the high quality processing, we are able to to do today is deghosting, designaturing. We have high quality processing, really efficient for sedimentary layers. But sedimentary layers are not our target. Our target is the pillow basalt just below the sedimentary layers. And what we can see here is that in the pillow lava, the image is not really good. We have instability in the signal, and the main issue is that in 2D, when you acquire a data, you have many out-of-plane seismic reflection and diffraction. And that's really tricky to deal with in 2D because you have no idea. And the result is that you can't see really precisely the limit of the basaltic layers that are our target. So the only solution to overcome this problem is going directly to a 3D seismic acquisition. So 3D seismic acquisition will give us the quality required for offshore geothermal prospection, and in addition, it will cover vast area. So we will have a 3D image of our reservoir, and we will need this 3D image to understand the system directly. So just to conclude now, offshore geothermal can help in building a sustainable future. And I won't go into the detail, but it's directly in alignment with the UN goals. Mariane touched on that this morning as well. So the Sustainable Development Goals, and we have every single element of that. And for that, to be sure, we need to define guidelines and recommendations to have assessment of the environmental impact for sure, documentation and research protocol, exploration, responsible exploration and development, and cultural integration and equitable development. And I will just finish on this slide. I think it's time to collaborate to be able to compete later on offshore geothermal. Thank you.
Thank you, Mariane.
You are fine.
Thank you, Mariane, for a very exciting lecture. I think this is extremely exciting. This is innovative. This is a new area. We know that there's a lot of potential out there. The question is how to get there. I'm going to allow one or two quick questions if someone has a question. Okay, if you have a strong voice, that's fine. But I have a mic here.
Yeah, hi, thanks. A very exciting talk. A lot of potential. I think I'm one of the few people in the world that's actually drilled into the ocean crust 3 times, into the layer you're talking about. The problem is that once you get into the pillow basalt layer, within about 100 meters, the permeability just shuts off. So I think that you need to consider what your reservoir looks like once you get down there, right? But it's there is very little information, but there is some information on that, and it's basically due to the secondary minerals that form as the crust cools, basically.
Yeah, thank you. Yes. So you were a part of the ODP or IODP projects, I presume. So it's very interesting. And that's why, and I think it highlights the importance of relevant workflow for exploration, data acquisition. For the world first, we need to have a full image and a really good image of our system to understand it and to know what will be the best target for offshore geothermal.
Thank you for an extremely exciting talk, and I think this is really the way of the future. Sort of just to reiterate and to ask, what do you think, how do you think we can move forward? What do we need to do? Because it sounds like we know how to do exploration on land. We know what we're looking for. We know what the anomalies look like. In the ocean, it's not exactly the same. So I'm just wondering, like, do you have any idea in your head how we should move forward as a community? And what do we need to do?
Yeah, thanks, Ausis, for that question. So actually, yes, we need to go forward. For that, we need to start the exploration. Start the exploration with 3D images of our reservoir with data acquisition. So acquiring a 3D seismic is key. And then we can add other geophysical methods such as EM, MT, CSEM, or whatever, just to image the fluid temperature and the hydrothermal. Combine the inversion with two of them. Try to identify where are the faults, where are the main circulation, what could be the temperature, and for that we will have indicators such as leakage at the surface, but leakage are probably, they are indicators of the reservoir, but probably not the best target for two reasons. First, for environmental reason, because around the hot spring we have offshore, there's a huge amount of life we know nothing about, so we better to avoid this area. But if we can sample the water and the brine in that, we will have an idea of the temperature of the reservoir, of the nature of the reservoir. So it's in parallel different things. Acquiring 3D images of our reservoir, punctual data sets, and trying to put all of that together in a model to understand the system and to have the best well targeting process.
Thank you very much,
Thanks.
Mariane. Next one is Rob Klenner. He is the Director of Geothermal Technology and Innovation for Baker Hughes. He has 15 years of experience as a part of a global team that leads Baker Hughes geothermal business and to enable growth opportunities in the geothermal market and the commercialization of subsurface to surface technologies. His lecture today is on closed-loop geothermal systems, an application for revitalizing mature geothermal fields. Is this working now? Nope. We'll have to use this.
All right. Is this on? Thank you. All right. Thank you, everyone, and thanks for the introduction. It's a pleasure to be here today. As mentioned, I'll be talking about closed-loop systems, another innovative technology where we've partnered as well as our investment in a company called Greenfire Energy. I'll talk about the different applications, why it's an interesting technology, where it's being deployed today, what we're doing on it, testing capabilities, and how it can serve and develop the market for the future. So just to step back, and thanks, Mariane, for the presentation and giving some context too on geothermal, how to develop it, and the opportunities as well. But just wanted to step back, and these numbers are a little bit different than that were presented this morning. So very in line of what we have as total capacity today with 16.8 gigawatts of electric installed capacity, with expectations to grow up to 17.7 gigawatts by the year end. Predominantly, if we think about the future of new technologies, so by 2035, still developing hydrothermal, geothermal resources with potential of growth, with 10% being supplied by new technologies, which we think of engineered or enhanced type geothermal systems, or closed-loop geothermal systems that most people refer to as advanced geothermal systems, although I think of it as a necessary enhanced geothermal technology as well. And then as we continue to project out about 25 years from now, most market analyses we're looking at 50% of the growth of geothermal, almost 10 times of what we have installed today, with 50% of that being contributed to these EGS, AGS technologies, as we start to develop and deploy these in other parts of where we don't have geothermal developed today. So over the past, since 2000, I kind of have this graph on the upper right-hand corner. Predominantly growth has been in the the Middle East, mostly in Turkey, and then also places in Europe, Iceland, of course, most of that as part of the market, and then some growth, as you can see on the bottom, with development out of Central America too. So geothermal projects in the United States, where I'll talk a little bit more about one of Greenfire's first deployments of this closed loop based system. But it's a very, very important slide as we start to think about geothermal resources. So, of course, geothermal is very sustainable, but at the same time, issues such as pressure depletion or other issues with wellbore and scaling can start to affect your overall resource. You have different decline, you need to drill up makeup wells. So most of the wells over the past 20 years, about a third of these have been drilled in the United States, but you can see there's been little growth, only about 800 megawatts out of all those continued wells that were drilled over the past 20 years. And about 500 wells, I think, drilled since 2000. So some added capacity, but due to reservoir decline, still have a large impact on continuing and developing growth in a great resource we have on the western part of the United States. Of course, there's been other developments as far as geothermal. On the enhanced geothermal side, where we're drilling doublets and having hydraulic fracturing to connect those reservoirs and create areas where traditionally hasn't been developed for geothermal in the past. But today there's also a lot of idle or abandoned wellbores. So wells that sit idle that have a very good heat resource and a steam-dominated resource, and then abandoned wellbores that can still be utilized using closed-loop-based technologies. So one of the things, if you don't think about, production decline does happen in geothermal fields, much like it does in any other type of reservoir. So even my son yesterday talking to me, interested in energy, he's only 11 years old, and he asked me the question, he goes, "Dad, are we going to run out of fossil fuels?" So I said, as a geologist background, I kind of have to say, well, technically no, if we leave a lot of the oil and the gas that's down there. And it's very similar when you start to think about geothermal with the heat and the resource that we have available, but the medium to extract it, we also deplete in many different ways. And that can be due to pressure decline, whether that's on well productivity and issues that are caused by heterogeneity, or else we have exploration issues where we don't necessarily get the production out of the well that we actually anticipated. Pressure reduction also affects the fluid production, as I mentioned, well spacing and how we have these wells spaced out and competing against the flow regime that we're working in. And then just permeability changes too, whether it's on the fractures, could be changes geomechanically too, based off of any local faulting, seismicity issues that can change also the impact of the production, and just other issues that can be caused, such as scaling, as I mentioned. So on the right-hand side is actually not necessarily a geothermal viewpoint, but more of an oil and gas viewpoint of how we start to think about new technologies and how we start to enhance production. So many people come up to me as well, not familiar with the geothermal industry, and they don't really understand what's actually being produced today in the geothermal market. And the first thing they say, well, does it work? And I'm like, well, we're doing it, all over the world, and but there's new technologies, I think, is what they're referring to, on how we get this heat resource out. And then the next questions are, well, which is the best technique, or which is the best technology? And I always, from my viewpoint, there's not a right technology, much like for the oil and gas industry. It's how do we use the right technology in the right reservoir? So there's different opportunities, and I think, closed loop geothermal systems isn't just the solution for enhanced productivity, but one of the tools in the toolbox we can start to use when we think about how can this be applied in existing geothermal reservoirs, or where we have a resource that we know that's hot, but we may not have a steam-dominated resource or the fluid that we can extract and bring to the surface. So as I mentioned, we've invested in a company called Greenfire Energy, and some of their representatives are here today. This is a closed loop solution where it uses a working fluid. It's a tube-in-tube heat exchanger. So as you can see on the right-hand side here, we have the blue lines which are going down. That's the working fluid, or the fluid that we're working with, which could be water, it could be supercritical CO2, or it could be a ORC-based fluid that's compatible with the surface-based system to generate electricity. As it's being injected, it's heating up. None of the fluid is actually going into the reservoir, but it's interacting with whatever fluid we may have within the wellbore itself. So it's still open to the reservoir, whether that's open hole or some slotted liner to interact with either the fractures and the permeability of the reservoir and any steam or liquid dominated resource that we have there, so that it's not purely conductive, but we also have ongoing operations in and around this heat exchanger. So as it's heated up, it's being produced back to the surface. Maintaining that heat production back to the surface is critical. So using things like vacuum insulated tubing, where you have good insulation to bring that high temperature fluid back to the surface. And there it's used for whatever needs you have, whether that's electricity generation or for other direct use applications. And then as around this heat exchanger, as steam interacts with it, you have condensation that's occurring that gets re-injected back into the reservoir, and you have some of these local convection effects in and around. So it's not a purely conductive rock to heat exchanger type solution, but there is some convective processes, especially if you have ongoing production in the same reservoir, that actually improves the overall output of this type of system. So from an environmental consideration, it's also a very good technology when you start to think about the type of emissions. So because it is closed loop, we're not actually extracting reservoir fluid and bringing that back up to the surface. So even in the maintaining reservoir pressure, we're not extracting any mass from the reservoir as we bring it back to the surface. So maximizing reservoir pressure in and around your existing operations. Land usage, much like any other setup, we just have a well, we have a small pump, and then the flow lines in and around that for the re-injection and production system, and if possible can use the current surface infrastructure when it comes to the power plant itself, if there is one. Induced seismicity, there's lower risk of using for induced seismicity. So in a place like we're considering with the current project at one like the geysers in California, a lot of induced seismicity occurs with the injection and production of these types of operations. Of course, when you're starting to mess with pressure changes within a reservoir, that will cause some induced seismic events. Here we're not impacting any of the pressure, so really a reduction in the overall induced seismicity effects. And then wildlife preservation, of course, no production again back to the surface, so mitigating a lot of those. So as far as project portfolios, it's always good opportunities to look at where we can deploy this. Working with Greenfire, there's many different projects. We're leading the laboratory side of things when we're scaling this type of technology. Gathering information and data of how we're extracting heat within our flow loop is something critical to what I'm doing and leading with our Wells to Watts consortium. But Greenfire has several different publicly announced projects, whether that's Calpine at the geysers, funded by California Energy Commission funding. There's other projects in the work with direct air capture in California of how you utilize the same technology with a direct air capture plant and waste heat recovery, and that'll be funded with by the Department of Energy. Other projects are looking at how you can actually scale this technology on a more greenfield type aspect where you can drill behind the meter. So it's also a good opportunity where you may have an existing infrastructure or city, and you may not have the steam dominated resource again, but you could drill a well right next to the facility that you're developing and create greenfield opportunities too. And then two other projects with KenGen at the Okira field and then EDC at the Mahanadong field. So of course, all these systems are complex. So A lot of times people model these and they're looking at more of a just purely conductive type model. But really you have to take different aspects too, especially the feed zones when we think about the geothermal fluid on the left-hand side there, and how that's going to be impacting in and around this heat exchanger system. So there's several different variables to consider when we start to think about these AGS systems, not just the surface system and the re-injection and the production of this closed loop, and how that's going to impact your overall heat to power. The working fluid and different types of working fluid that we can use, and how that's going to impact whether that's a hydrocarbon or refrigerant-based fluid, supercritical CO2 or water. And then also the subsurface conditions that I've mentioned many times, but not only just the liquid or the steam and the quality of the steam within the subsurface, and the several different feed zones, and then any other ongoing production and injection operations in and around the areas that you're looking to deploy, where you may actually have this system. One of the things too is, as many people think about, you can model these out a number of times over. One of the critical things that we're working with, and we're working with some major oil and gas players in the United States, was to build out a flow loop where we've deployed this at a very small scale. When I say small scale, it's a 300-foot flow loop that we have as part of Baker Hughes. What we had to do is, of course, at 300 feet, we don't have a very high temperature gradient. So we have several different casing configurations here. We have a 20-inch diameter well. Within that, we have 16-inch. We've pulled a vacuum on that so we don't radiate any of the heat back into the subsurface. And then around the 9 5/8, which is that red casing, we've wrapped several heater coils around that, and we're able to heat up this well. Actually, the heater coils can get up to 400 to 500 degrees. So that gives us a high reservoir temperature. Within that, we have a transfer liquid, and then we have the downbore heat exchanger, which is a 7.5-inch and then a 4.5-inch vacuum insulated tubing inside of that. So we have a pump at the surface where we're able to configure and look at different flow rates. And this has enabled us to gather several data points and information that we can now calibrate and tune our models and start to think about how to scale that up, but also look at different working fluids in the future beyond just water at the moment. This is the final test setup that was installed. On the left-hand side is the configuration for us to just diagnose and understand the health of the system as we're flowing through, looking at the pumps, how many gallons per minute are we flowing through here. We also have several different heater zones. So we have 5 different heater zones that we're monitoring that we can keep consistent temperature. But we're predominantly putting down almost 750 kilowatts of energy downhole to heat this up. So of course we're losing a lot of energy to understand or to put down because we don't have the heat there. But the heat will allow us to extract that out, and we can start to understand the thermal efficiency out of this system. So you're probably wondering how much energy can we actually get out of these types of systems. We've done several modeling. With Greenfire, we've looked at different reservoirs for a statistical evaluation. And of course, it really depends on those variables that I mentioned before in and around the reservoir, and how you have that cross flow, the wellbore diameter, and the type of working fluid. But with high temperature systems where you're looking somewhere between 200 to 300 C, you're going to get anywhere from 1.7 to 2.1 megawatts of electrical potential using this type of system. Of course, that can vary on a very site specific. The wellbore length, as I mentioned, any other scaling issues or any other issues that you may have had in the well before could affect it as well. Reservoir transmissivity, the feed zone depth, heat flow, and overall pressure in the system. So it's a good and viable solution. Of course, it's may not be the same exact outcome you would have if you actually had a a producing well with steam, but it still gives you a viable option over time as you start to complement this with your existing geothermal reservoirs. So if we think about this technology and what can be used today, just looking at the United States, as I mentioned, where we have idle well bores and abandoned well bores, very high potential when it comes to that 1.5 to 2 megawatts per well. We could essentially double the output of what's capable in the United States today with our existing capacity of just over 3,800 megawatts. So it's a very good solution when complemented with existing geothermal reservoirs. And maybe for Iceland too, thinking about not necessarily lots of idle well bores today, but how we effectively manage a reservoir. How is this overall going to impact reservoir decline over time and complement existing geothermal development, but also in other areas where you may have some high temperature resource and you may not have the steam production that you thought you would. It could be a good opportunity to augment this with existing operations. So just in conclusion, it's a attractive opportunity, especially when you start to think about leveraging existing wellbores because your capital cost is very low. We've seen attractive economics just in US dollars between 2 cents up to 5 cents. Of course, if you're going to have to drill or work over the well, those will start to go up as far as the cost itself. As far as permitting, this is a good opportunity too, where you don't have to do a lot of additional permitting to drill a new well or infrastructure. Performance is very predictable because you know the flow rate that you're working through here. You can vary that flow rate to extract, at different temperatures at the wellhead that you're looking to get to. And it's also, cost competitive with other renewable technologies. So anyway, hopefully that's a good introduction to the new technology of advanced geothermal systems and the opportunities it could provide in mature fields. Thank you.
Thank you, Rob, for a very interesting lecture. I believe this is one way to go about our resources without exploiting them too much. But I'm going to allow a couple of questions if there are any. Okay, over there.
Thank you. Tara Rogers with Clean Air Task Force. When choosing your reservoir temperature range for modeling your power output, why did you stop at 230 Celsius? And is there a hypothetical model that might get us closer to 400 or 500? If so, how would you have predicted the power output?
Yeah, so a lot of the models were with, keep in mind, the retrofitting type opportunities and using existing geothermal. Several models, we've looked at higher temperature resources, 400, 500, 600. So we have different results from that. The challenge you start to run in with the hot dry resource too is you don't have that convection happening in and around these type of well bores. So one of the key aspects and very target focused right now is existing geothermal reservoirs and how to use this in where you already have a steam dominated resource interacting with the heat exchanger. But of course you can use the same technology. You have some reduction in risk too with maybe some other type of advanced geothermal systems where you have to connect two different or more U-loop type configurations. And so you can do the same thing in high temperature as well.
One quick.
Thank you. That's a very nice presentation. My name is Frederick Apollo from Kenya. I'm just concerned, what's the likely to be the impact on the net power output, considering the fact that there's going to be an inclusion of the injection pumps that's likely to increase the parasitic load?
Yeah, actually the net output was what I showed. The parasitic load is very, very low with the pumping system. So we it's on the kilowatt scale. So we don't need high horsepower pumps for this type of system. So there's very little pumping requirements when it comes to this overall.
Okay, thank you, Rob. You can continue discussing this over lunch. Next one. Next presenter is Anna Sowiżdżał. I hope I pronounce it correctly. Her lecture is about the study of feasibility of enhanced geothermal systems implementation in Poland. Anna is an associate professor at the HGH University in Krakow in Poland, a project manager of the Energizers project concerning the analysis of effectiveness of enhanced geothermal systems with CO2 as the working fluid. This one maybe.
Thank you very much. Yeah, okay. Good morning, ladies and gentlemen. As I was introduced, I came here from Poland, from Krakow, from HGH University. This is one of the biggest university in Poland and modern technical university. We educated students in case of geothermal energy and also carried out some research work to develop geothermal energy in Poland in cooperation with other Polish institutions and also with cooperation with industrial partners. Of course, geothermal energy utilization is mostly affected for geological conditions. And Poland is mostly built from sedimentary rocks, so the sedimentary basin are the first reservoirs for geothermal energy. Only in west part of Poland, there also some crystalline rock occur. Poland also has natural resources of coal and lignite, and despite that now the share of renewable energy sources in Poland's energy mix is increasing, we still use a lot of coal and lignite for power and heat production. It's a big problem in Poland because it's affected of air pollution in our cities. Krakow was the first city in Poland, and I think only one till now, which introduced ban of fossil fuel burning. And we are aware that we need to find some solutions, some new innovative solution, how we could progress development of renewable energies, including geothermal energies. We need to find new technologies to give the society the tool to change this coal burning for another environmental friendly source of energy. In Poland, we have only low enthalpy hydrogeothermal potential. It's not, of course, like Iceland. We have no high temperature geothermal fields, but we can use low geothermal potential to use for heat. And till now, we're using this potential in seven heating plants. The biggest area with the most prospective province is the Polish lowland. This is the blue one. There is 6 of 7 existing heating plants. And the second one is Podhale region in the south part of Poland. The oldest one and the biggest one heating plant exist. But it's still not enough. We need more heating plants and we need to find a new solution to develop geothermal resources. The geothermal reservoirs with commercial significance till now, it's only lower Cretaceous and lower Jurassic formation in this Polish lowland, as well as reservoirs connected with Podhale area. Till now, no enhanced geothermal system exists in Poland. But from 2010, we carried out different works to find solution, how we could develop this petrogeothermal potential in Poland. Because the big problem with geothermal utilization in Poland was the flow rate of the wells. So we find that we need to look for another solution. We have some area with very good thermal conditions. It's connected with this west part of Poland, and we need to think about possibility to introduce new and innovative technology like enhanced geothermal energy. And today I would like to say a few words about project, Polish-Norwegian project called Energizers, as well as other our EGH project connected to the development of geothermal energy in aspect of petrogeothermal resources utilization. Till now we find 5 very interesting area to introduce this enhanced geothermal system with different temperature on different depth of reservoirs. Of course, we have in Poland another thermal condition than here in Iceland, so the temperature won't be so interesting and so high as here. The Energizers project, the full name is CO2 Enhanced Geothermal System for Climate Neutral Energy Supply. It's the project which has received funding as part of the Polno 2019 Polish-Norwegian Research Project, financed under Norway grants via the National Center for Research and Development in Poland. We work together with 5 partners. 2 of them was from Norway, it was SINTEF and NTNU. We also cooperate with Polish Academy of Science, and our industrial partner was Exergon. The project finished on the March, so we now have results of this work. And the main idea of this project, it was progress the technology of enhanced geothermal system, but using carbon dioxide as working fluid. As I said before, we have a big problem with air pollution, with greenhouse gases, and CO2 is of course one of these gases. So we look like for solution to compare 2 aspects. Of course, for us, the main important was energetic purpose, but the second very important aspect was find solution to do our environmental more clearly. So this environmental purpose connected with CO2 sequestration. We hope that some part of CO2 will be stored in reservoir, and also the CO2 will be the medium in this EGS system. Of course, we was looking about the worldwide experiences. We didn't find a lot, but I know that there is now a lot of project to start thinking also about this solution. And we hope that also in Poland will be part of this, of the implementation of such project. Of course, we cooperated with our Norwegian partner. It was a very good situation to exchange the knowledge about this CO2 utilization as well of geothermal energy development. We take into account the first geological criteria, but we were looking for rock with very low permeability, but not so low like in classic EGS where water is a medium, because we would like to store some part of CO2. So the reservoir should have very low permeability, and of course the thermal aspect is very important. The highest temperature of reservoir rocks is the best solution. We find this area in the west part of Poland. Gorzów Block area was indicated as the best one, and the second area is connected with central part of Poland. We did it using some method of matrix of influence, asking experts about some very important aspect to locate such installation. Gorzów Block was the key area for us, so we carried out some laboratory tests for finding the petrophysical aspect of rock, and we find Ośno IG2 well as our well to test. And the reservoir rock will be connected with sandstone and extrusive rocks. We also find worldwide solution, and Großschönebeck installation, which is located very close to Poland, to border of Poland, was the inspiration for us. It's the same reservoir like in Germany, this lower Permian reservoir. We did some laboratory tests in AGS laboratory. It was petrophysical, mechanical, thermal, and mineralogical test of these rocks to find the information, what kind of rock is there. And we compare these parameters to parameters of rocks to in Großschönebeck, and we found then this lower Permian reservoir is good for our solution because of these parameters of permeability as well as porosity. And in this location, we prepare some case studies. Today, I only will say about Polish case studies, but I think that it's also interesting that our Norwegian partner find this location in like offshore system. So I think it's common also with this previous presentation. But we in Poland find this location in the onshore system, and we try to find different solutions. And the first one, case one, is connected with combined heat and power, and second case is connected with power generation only. A lot of modeling work. The first, of course, mathematical modeling of geological reservoir. We prepare some 3D structural parametric model using Petrel software, as well as conceptual model. Very important aspect is, of course, fracturing process in this INGS system. We prepare modeling of fracture, and we found that distance between wells should be about 600 meters. It will be optimal for the solution. And at the end, it was 3D numerical model for multivariant simulation. This is the conceptual models prepared by our partners, Polish Academy of Science, led by Maciek Miecznik. He's present also here. And we find that expect reservoir temperature is about 145. We are aware that it's maybe not so high like it should be, but it's the best, I think, in Poland. And the total depth of this reservoir is something around 4,300 to 4,100 above sea level. So it's the temperature connected with this geothermal reservoir. We prepare also topside modeling, and we find that it seems possible to combine the development of geothermal and carbon capture and storage technology in case to reduce carbon dioxide emissions, what is a very important aspect in Poland, and also for cost-effective generations of heat and as well as electricity if possible. In our two cases, it was a different scenario. In the first cases, we find that it's possible to have electricity power 0.4 megawatts and 9 megawatts for heat power for up to 18 years. And in case 2, power generation case only with hybrid cell, we found like 1.7 megawatts electric power for up to 20 years. And this is the first estimation of cost, and of course it's really important, and we are aware that it's could change. It's what we found. We were aware that this installation is costly for our economy, but what we found that energy prices grow up at the market. It was more efficiency here in this solution. And it was surprising for us that the most income came from CO2 storage and heat production, because the first our thinking was that it will be connected with not heat but energy, electricity production. And of course it will change on the time, but the result I think was positively surprising for us. So we will hope that it will be the positive aspect to maybe introduce some solution in Poland. And to the end, it was also some environmental research, also connected with the work realized, but AGH with PhD students is the base for the PhD thesis. They prepare life cycle impact assessment using CIMAPRO software, and we find that the biggest environmental impact is of construction phase, and the very low impact on the operation and maintenance phase. And of course, a lot of greenhouse gas emission was avoided to using such solution. And at the end is the result of our work, and of course, we are aware that we are at the beginning of this this adventure of enhanced geothermal system. I also hope that another more experienced people maybe could join us to develop this solution in Poland, because it was first our research connected with this EGS using CO2. But I hope that maybe in the future will be the also option in Poland for hydrogeothermal energy. A lot of positive aspects connected with training of young people, involving them in our experiences, involving them in our research. One of my students took internship 6 months in Norway, so I think it was very great solution and opportunity for them. So thank you very much for your kind attention.
Thank you, Anna, for yet another innovative solution to all our problems, hopefully. I will allow 2 quick questions if...
So Alterac did a lot of work on CO2 for EGS, and one of the things we found with our modeling work was that you're going to have water, and that's going to mix with the CO2 and make carbonic acid, and you're going to produce that throughout the life of any project. So you're going to have to go to really, material selection to avoid the corrosion. Have you looked at that and how that's going to impact your economics?
Yes, we are aware that there will be a lot of problem also with corrosion as well, and impact in the reservoir rock. We have also problem in corrosion in case of hydrogeothermal utilization in Poland, and it's a big talk about it, how we should solve the problem. So I hope that it will also talk how we should solve the problem here in EGS systems. But in this particular case, it wasn't analyzes the aspect of the this technical aspect of these wells, but we are aware of it, and I know that it could be a problem also.
Another question?
Thank you. My name is Floris Figger, working for Sproul in the Netherlands on a lot of operational projects, and we've done some similar studies in aquifers and even applied a little bit of it to as a kind of pilot plant, not published. But I'm also wondering, in line with the previous question, what ratios you want to apply in CO2 versus water, and also the material selection itself. Yeah.
Okay, we did some analysis because this internship, which I mentioned, was connected with this CO2 aspect because our partners from Norway have a laboratory and we find the best solution. And we also check some different mixes of the phases. And but in our analysis, we think that it will be mostly CO2, that the additional to water will be not so many. It will be, I think, like 90% of CO2.
Okay, sorry. And the second part of the question was why do you focus on EGS and not on the natural matrix, which is already in the case in many projects in Poland at the moment?
Yeah, because we have a lot of experiences with hydrogeothermal resources, but we know that in some wells we have problems with water, and we have some dry wells, and we need to find solution. What will be in this place, in these cities, where is not potential for water, for hydrogeothermal resources. Not every cities have this big potential of hydrogeothermal resources. It's only limited space, or limited area where water is enough to build such installation.
Thank you very much, Anna.
Thank you.